To begin this lesson, I just want to talk a little bit about the language around radicals. So the part of the radical that is inside the radical itself is called the radicand. And of course we've got the radical sign itself. And then whatever type of root it is, that is what we call the index. So for a square root, for example, the index is 2. For a cube root, the index is 3, and so on. So those are some important terminology pieces to understand as we work with radicals. Here we're just going to take a look at some real roots and talk a bit about how we get our results. So when we're finding cube roots of these numbers, really we're looking at what number can you multiply by itself 3 times in order to get these numbers. So this number here, which is really 8 1/1000ths, or 0.008 as we usually say, but it's 8 1/1000ths. So this is really, the cube root of that is 0.2. Now, again, for me it's a little bit tough to see that that is what it is. So what I look at is that number, again, as a fraction is 8 over 1,000, and I know the cube root of 8, and I know the cube root of 1,000. So cube root of 8 being 2, and cube root of 1,000 being 10, then I know that that's 2/10. Of course I could reduce that down to 1/5, but either way the decimal is 2/10. So that's how I can see that one. The other ones aren't too bad to see. For example, a negative 1,000. And important here that we can have a real cube root of a negative number. And that's because if you multiply negative 10 by itself 3 times, you have 3 negatives. 2 cancel out, you're left with 1, so you have the negative 1,000 as the result there. And so negative 10 being the real cube root of negative 1,000. And then looking at the fraction like the 1/27th, I would compare it to the 8 over 1,000. We can cube root the 1 and get 1, and cube root the 27 and get 3, because 3 times 3 times 3 is 27. And of course 1 times 1 times 1 is 1. So to me it's easier to think of it as a numerator and a denominator rather than the whole thing. So 1/3 is the cube root of 1/27th. Because if you multiply 1/3 by itself 3 times, you get 1/27. Now when we look at real fourth roots, big difference here is fourth roots are even roots. So we're going to have an even number of factors multiplied together. So with like a 1, for example, there's 2 real fourth roots for 1, because you can have 4 1s multiplied together to get 1. Or if you have 4 negative 1s multiplied together, you also get 1, because the 4 negatives all cancel out. So, on the other hand, when we try to find the real fourth roots of our decimal here, which would be a negative 1 over 10,000, there are no real fourth roots for that number, because we have 4 numbers that we multiply, or one number multiplied by itself 4 times. So we either have 4 negatives or 4 positives, all of which would turn out to be positive. So no real fourth roots for negative 1 over 10,000. Then we get to another fraction, 16 over 81. Again, I think of that as the fourth root of 16 and fourth root of 81. 2 to the fourth is 16 and 3 to the fourth is 81. So the fourth roots of 16 over 81 are 2/3 and negative 2/3 for those. Then a couple questions at the bottom, talking real fifth roots for 0, negative 1, and 32. So what number can I multiply by itself 5 times to get 0? Well, the only answer there is 0. What number can I multiply by itself 5 times to get negative 1? Well, that would be negative 1. And what number can I multiply by itself 5 times to get 32? So that would actually be 2. So 2 to the 5th power is 32. And then real square roots for 1 100th, negative 1, and this is 36 over 121. So 1 100th, again, if you think of that as a fraction, you can square root the 1 and square root the 100. You get 1/10. So that's the square root of 1 100th, or as a decimal, 0.1. There are no real square roots for negative 1 because it's negative. And to square root, or find the real square roots of 36 over 121. Right, again, I should have a positive and a negative, 1/10 really, for the first one. And square rooting the 36 over the 121, I get 6 over 11, and again, because it's an even root and a positive number, we get 2 real roots, both positive 6/11ths and negative 6/11ths. One of the big things we want to be able to do here is to simplify radicals. In order to do that, we will use this property that says for any real number a, the nth root of a to the nth power can either end up being a if n is odd, or the absolute value of a if n is even. Just a couple simple examples there. If I have the cube root of x cubed, the result is just x. Whereas if I have the fourth root of x to the fourth, the result would be the absolute value of x. And again, the difference there is x to the fourth cannot be negative, and so when we fourth root the x to the fourth, we get a plain x, and so that should not be able to be negative either. Whereas if we have the cube root of x cubed, that can be negative. We simplify it to x, which can also be negative in the same case. So that's why we don't need the absolute values for the cube root of x cubed. So when we look at a question like the square root of 16x to the 8th, we can square root 16 well enough. We've done that for a while now, and we just get 4. There are a couple of different ways to figure out how to square root the 8. The way that I think is the simplest is to just understand that we're saying what can I multiply by itself twice to get x to the 8th. Well, if I multiply something by itself, it would have to be an x. So really I'd have to multiply x to the 4th by x to the 4th. Well, and the way that I really come up with the x to the 4th is I say, well, if it's got to be 2 of them, then it's got to be half of the 8. So really we're just dividing the index, in this case 8, by 2. So we do take just the regular square root of 16 and get 4, and we divide the 8 by 2, we get x to the 4th. Now this would technically be inside the absolute values. However, if we think of it, since x to the 4th can't be negative, we don't need the absolute values at all. We just get a plain 4x to the 4th because that has to be, or can't be negative anyway. Now if we look at the second example, we don't have any plain numbers. It is an odd root, so we don't have to worry about absolute values at all, again because n is odd. So we just divide the 6 and the 9 by 3, so we get a to the second power, b to the third power, and that's all we have to do there. For the last one here, again we don't have any numbers to worry about, but we just divide the 8 and the 12 by 4, so we get x to the second, y to the third. Now again, really it would all be in absolute values, but notice the x squared does not really need them, so we kind of pull that out and just have the absolute value of y cubed. And then I just have a few more examples here. So square rooting 81x to the 4th. Of course the square root of 81 is 9, and when I divide 4 by 2 I get 2. So again, and that would be inside the absolute values, but we would realize we don't really need them because x squared can't be negative anyway. For the next one here, the cube root of a to the 12th, b to the 15th, really just dividing the 12 and 15 by 3, so a to the 4th, b to the 5th. And no absolute values necessary because it's an odd root. And for the last one, it's an even root, so we'll have absolute values. And we'll just have to determine whether we need them or not. 12 divided by 4 would be 3, and 16 divided by 4 is 4. So we need those on the x cubed because x cubed can be negative if x is negative. We do not need them on y to the 4th because even if y is negative, then y to the 4th can't be negative. And these are the last examples I've got for you on this, so hopefully you're starting to get the hang of it a little bit. If we start with the square root of 25a to the 4th, again we would have absolute values. However, we end up with a 5a squared, so absolute values are not necessary. For the 4th root, we would also have absolute values. We divide the 12 and the 4 by 4. We get p cubed and q to the first. And you don't necessarily need the 1 there, but just to emphasize that that's a 1. Now those would both need the absolute values because they both ended up with an odd exponent. Let's see, for number 4 here, we would have to have absolute values around the 3b. Now the 3 does not really need the absolute values, so 3 times the absolute value of b. See, for number 5, we would also need the absolute values. We'd have a to the 4th, b to the 9th. So the a to the 4th does not need the absolute values, but the b to the 9th does. And the cube root is an odd root, so we don't need absolute values. Negative 125 would be a negative 5, and then just a plain a. And so hopefully that helps with simplifying some of those radical expressions.